In this video, we shall look at a couple of review problems on pendulum and oscillations. First, a brief introduction. Assume that you have a physical pendulum in the form of a uniform rod, like the one shown in the figure. Assume that this physical pendulum can swing or oscillate about an axis through this pivot, denoted by this white dot. So the oscillation is like that. Assume the mass of this rod is capital M and the length of that rod is capital L. Since it is uniform, the center of mass is exactly in the middle, so that distance is L over 2. This is just an example of a physical pendulum. Its period is given by the following expression: 2 pi square root the moment of inertia of this pendulum about that pivot point over the mass of the pendulum times the gravitational acceleration times the distance between the center of mass and the pivot point. Let's call it h. So in this case, h is L over 2. Let's apply this expression to a simple pendulum. A simple pendulum is a bob connected to a string. Let's assume the length of the string is L, the mass of the bob, where all the mass of the system is concentrated, is little m, and when you pull this bob to one side and then let it go, it's going to oscillate like that. So this is a simple pendulum. Let's apply this equation to this system. So the period of a simple pendulum is given by 2 pi square root. The moment of inertia of the system is just m times L squared. It is a moment of inertia for a point mass. So this is the point mass, and this is where the axis of rotation is, and the distance between them is L, thus ml squared for the moment of inertia. Divide by the mass of the system, in this case the mass of the bob, little m, gravitational acceleration, and h is the distance where the center of mass is. In this case the center of mass is where the bob is, and the axis of rotation. So the distance h in this case is L. So you see m goes away, this L will cancel that L, and you get the familiar looking equation for the period of a simple pendulum: square root L over G times 2 pi. Now let's get to the problems. Problem 1. The pendulum shown below consists of a uniform disc, so that's this one, with radius 12 cm and mass 520 grams attached to a uniform rod of length 0.5 meter, that is this one, and mass is 300 grams. Calculate the moment of inertia of the pendulum about that pivot point. So let's do part A first. Moment of inertia of the system consists of two parts. One is the rod, and the other one is that uniform disc. So let's do the rod. The moment of inertia of that uniform rod about an axis through its end, it's given by 1 over 3, the mass of the rod, m sub r, times the square of its length. Now the uniform disc. The moment of inertia of a uniform disc about that axis, which is there, is given by the moment of inertia of that disc about an axis through the center of mass, and that is given simply by half the mass of the disc times the square of the radius, plus the mass of the disc times the square of the distance between the center of mass and the rotation axis. In this case, it is r plus L squared. So this term plus that term is the moment of inertia of this uniform disc according to parallel axis theorem. Now let's put in the numbers. 1 over 3, the mass of the rod is 300 grams, so 0.3 kg that is. L is 0.5 squared, plus half the mass of that disc is 520 grams, so 0.52 kg. The radius of that disk is 12 cm right there, so 0.12 meter square, plus again the mass of the disk is 0.52 kg, and R plus L, R is 0.12 meter, L is 0.5 meter squared. And that's going to give you 0.229 kg meter squared. So that is the answer for part A. Now let's do part B. Find the distance between the pivot and the center of mass of the pendulum. So let's first determine the center of mass of the pendulum from the axis of rotation. The center of mass can be calculated using the formula that we have seen in our previous video, namely the mass of that disk times its distance from the pivot point plus the mass of the rod times its distance, or the distance of its center of mass from the axis of rotation. Let's call it R. And to that you divide by the total mass, the mass of the disk plus the mass of the rod. So let's put in the numbers. The mass of the disk is 0.52 kg. The distance of its center of mass, that point, to the pivot is R plus L. So R is the radius of that disk, 0.12 meter. L is the length of the rod, which is 0.5 meter. Plus, now the mass of the rod is given by 300 grams, so 0.3 kg. The center of mass of the rod is exactly in the middle, and the distance to the pivot is L over 2. So L is 0.5, half of that is 0.25 meter. Divide by the total mass, which is 0.52 kg plus 0.3 kg, and you're going to get 0.485 meter. And we have recorded the answer for part B there. Now we are ready to determine part C, the period of oscillation. The formula is given by the following: the moment of inertia over the mass of that entire system times the gravitational acceleration times h. H is the distance between the center of mass of the system to the pivot. And we have determined this in part B. So h is indeed 0.485 meter. So let's put everything together. 2 pi square root. I is 0.229. That is from part A. Over the total mass is the mass of the disk plus the mass of the rod. So 300 grams plus 520 grams, so that's 820 grams, 0.82 kg, times G. G is 9.81, and H is 0.485 meter. And now you can calculate the period. When you do that, it turns out the period is 1.52 seconds. And that solves the problem. Problem 2. Figure below shows a physical pendulum in the form of a uniform solid disk of radius 2.5 cm. So capital R is 2.5 cm. It is pivoted in a vertical plane at a distance L, 2 centimeters. So that is the pivot, and the distance between that pivot and the center of mass is 2 cm. If the disk is displaced by a small angle and released, it oscillates, like that. Find the period of the oscillation. Since this is a physical pendulum, the period is given by the following equation: moment of inertia over mgh. So first, let's determine the moment of inertia of this disk about that pivot. It is given by the parallel axis theorem. So it is the moment of inertia of that disk about the center of mass, which is given by half times the mass of the disk times the square of the radius, plus the mass of the disk times the square of the distance between the center of mass and the axis of rotation, in this case L, so L squared. Let's substitute this expression inside that equation. You will get the period equals 2 pi square root I is half the mass of the disk radius squared, plus again the mass of the disk L squared, over, now this m is the mass of the disk, which is m sub d, g is gravitational acceleration, and h is the distance between the pivot point and the center of mass, in this case just L. You see the mass cancels out, so you don't really need to know what the mass of the disk is, and you know all the other parameters. And let's calculate that. T is 2 pi square root half capital R squared. R is the radius of that disk, 2.5 cm. Turn that into meter, 0.025 meter squared, plus L squared. L is 2 centimeters, so 0.02 squared, over G is 9.81 times, again, L, which is 2 centimeters. Convert that into meter, and that should give you period in seconds. When you do the calculation, you get the following: 0.379 seconds. And that solves the problem. Thank you for watching.